My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn the advantages of an AC current over DC current. Also, we'll learn about the hot wire ammeter, the use of the device, its idea, mode of work, and we'll make a comparison, very important one, between moving coil galvanometer and hot wire ammeter. So let's get started. AC circuits. What's meant by an AC circuit? It is the circuit which is powered by an AC dynamo. And of course, you know, an AC dynamo generates an AC current. So let's define an AC current. What's meant by AC current? Okay, in front of you we've got a definition for the AC current. What about it? It is an electric current which varies in strength. Okay, and what about its direction? It periodically reverses its direction. It is shown in front of you by the diagram. Also, it could be represented by a sine wave. We usually say it changes sinusoidally. Okay? And the question now, is there a relation between frequency of the current and frequency of the dynamo which generates the current? First of all, let's define frequency. Frequency of the AC current is the number of complete cycles made in 1 second. So, once again, it is the number of complete cycles made in 1 second. And of course, unit of frequency is hertz, cycle per second, or revolution per second. Okay, and what about the frequency? It is exactly the same number as the number of revolutions made by the coil of the dynamo which generates the AC current. Of course, same revolutions made in 1 second. So this was about the AC current, definition of AC current, and frequency of the current, which is equal to the frequency of the coil, the frequency with which the coil of the dynamo is rotated, which is the number of revolutions made in 1 second. And now there is something very important here. Okay, it is about the advantages of the AC current over the DC current. Okay, we'll take it one by one, and it is very important. AC current can be generated at high voltage. It means the voltage could be increased or decreased using, yes, transformers. So an AC current can be generated, yes, at high voltage. So it can be transmitted efficiently through power lines over long distances without much loss. And this is very important advantage. Also, an AC current can be stepped up or down as needed by using electric transformers. The voltage can be stepped up or down. And of course, when we change the voltage by using a transformer, the current also changes. And I just want to remind you with something. Yes, a step-up transformer for voltage is a step-down for current. Also, AC current can be converted into DC current, can be rectified. Okay, so it's all easy to convert an AC current into DC current. Both AC and DC currents have thermal effect when passing through a resistor. Let me say it again. AC and DC currents have thermal heat effect when passing through a resistor. The power of the AC current is not consumed in coils and capacitors. Okay, let me say it again. The power of the AC current is not consumed in coils and capacitors. That's to say, no electric power is dissipated in form of heat in coils and capacitors. In coils when they are pure. And now talking about the hot wire ammeter. Of course, you are familiar with the moving coil galvanometer used for measuring currents. Okay, and now we are talking about hot wire ammeter. We'll start with the structure. Okay, in front of you there is, yes, a hot wire ammeter. And what about the use of the device? Okay, it can be used for measuring the effective value of the AC currents and the direct currents. Okay, this was about the use of the device. It can be used for measuring the effective value of the AC current, and it also measures the direct current. And now we'll talk about the structure or construction of the device. So, construction and operation of the hot wire ammeter. Okay, we've got a thin wire in front of you, is shown, denoted by letter H, capital H, and the thin wire is stretched tightly between two fixed ends A and B. Okay. And the wire is made of platinum iridium alloy that expands remarkably. Okay, so it is made of platinum iridium alloy that expands remarkably when heated by electric current that passes through it. It means the device is based on the thermal effect of the current. That's why it can measure, yes, DC and the effective value of an AC. So one important point of difference between moving coil galvanometer and hot wire ammeter is the idea. Okay, moving coil galvanometer based on magnetic effect, but hot wire based on thermal effect. Okay. Also, we've got a silk thread denoted by R. One end of the silk thread is tied to the middle of the thin wire, and the rest of the wire is wound once around a pulley denoted by P that can rotate about its axis. The pulley is attached to the pointer of the instrument. The other end of the silk thread is anchored to one end of a spring. The other end of the spring is fixed. And now talking about operation of the device. When the current to be measured, so talking about mode of work, when we want to measure it, when the current to be measured is passed through the device, the platinum iridium wire warms up and sags. What does it mean, sags? It loosens, it expands. Okay. The sag is taken up by the silk thread, which is held taut by the spring. The pulley rotates, and so does the pointer. Pointer is attached to the pulley. So when the pulley rotates, the pointer moves. The deflection of the pointer, this is very important, is proportional to the average rate at which the heat is developed in the wire. Deflection of the pointer is proportional to the average rate at which the heat is developed. It is therefore proportional to the average value of the square of the alternating current. And the scale is a square law scale. We call it square law 1 or square law scale. So it's not uniform. Okay, this is very important. But the scale of the galvanometer is uniform. In the galvanometer, angle of deflection theta is proportional to the current, but in this device it is proportional to square the current. And now we've got something to mention, important hints. A moving coil galvanometer can be used to measure, yes, cannot be used to measure an AC current. It can measure DC current, but cannot be used to measure, yes, AC currents. The question is why? Okay, we'll answer this. If an AC current is passed through a moving coil galvanometer, what happens? The pointer of the galvanometer does not move. Okay. Why? The coil is urged clockwise and anti-clockwise at the frequency of the current and does not move at all. This if we use the device, if we use the moving coil galvanometer to measure an AC current. Okay? The pointer of the device, okay, the pointer should deflect in a given direction on the positive half of the current, okay, and reverse its deflection on the negative half of the current. But the coil cannot oscillate with the same frequency of the current, so it just records the average value of the alternating current. And of course, you know, the average value of the alternating current, okay, in one cycle is equal to 0. Okay, we've got another piece of information. It is about the hot wire ammeter. Hot wire ammeter is calibrated by connecting it in series to a moving coil galvanometer. So we mentioned two things. First of all, we cannot use the moving coil galvanometer to measure an AC current. Okay, it will record 0. Okay, and we explained this. And hot wire ammeter is calibrated by connecting it in series to a moving coil galvanometer. Okay, when current is passed through the resistance wire, this is about the mode of wire, the wire warms up to a temperature such that it loses heat, so it warms up to a temperature. Its temperature increases, okay, till it reaches a temperature at which, yes, it loses heat at a rate equal to the rate, yes, of heat developed in the wire. So temperature settles. Okay. And now talking about the disadvantages of the hot wire ammeter. So once again, yes, we are talking about disadvantages of the hot wire ammeter. First of all, the pointer deflection is so slow when the current to be measured is passed through the device. So it takes time to measure. Okay, this is one thing. Also, the pointer takes time to return to 0. The pointer returns slowly to 0 scale when the device is disconnected, when we finish measuring the current. Okay, we're talking about disadvantages of the hot wire ammeter. Atmospheric temperature temperature of the surroundings affects the expansion of the resistance wire, and this may cause a zero error. This is another, yes, point of, yes, defect here. To eliminate this effect, the resistance wire is mounted, is placed on a plate made of platinum iridium or any metal having the same, yes, same watt, same expensivity. In this way, the wire and the plate expand equally, keeping the wire with the same tension, keeping the wire with the same initial, yes, tension. And now we've got some give reasons. In the hot wire ammeter, a wire of platinum iridium is used. Why made of platinum iridium? Why the wire is made of platinum iridium? As I said, the platinum iridium alloy has high coefficient of expansion. So it shows considerable expansion when a current passes through it. Another give reason, the scale of the hot wire ammeter is not uniform. This is one of the most important give reasons here. The scale of the hot wire ammeter is not uniform. Okay. The function of the hot wire ammeter depends on the thermal effect of the current. Okay, thermal effect of the electric current. And what about thermal effect? Thermal effect of the current is determined from the relation I squared R. It is power of the wire. Yes, it's power to convert electricity into heat, and it is determined by the relation I squared R. So the deflection of the pointer, denoted by theta, is directly proportional to the average value of the square of the alternating current. Theta is proportional to I squared, and this explains why the device is not uniform. Scale of the device is not equally spaced, evenly divided. It's not uniform. Another give reason, the hot wire ammeter can measure both AC current and DC current. We can use it to measure AC and DC currents. The function of the hot wire ammeter depends on thermal effect. Okay? And AC and DC, both of them have thermal effect. Okay? Both AC current and DC current have thermal effect, so they can be measured by the hot wire ammeter. Another give reason, the hot wire ammeter is provided with an adjustment screw to adjust the pointer to zero scale. Let me say it again. The hot wire ammeter is provided with an adjustment screw to adjust the pointer to zero scale. The resistance wire is affected by changes of the atmospheric temperature. So its pointer moves away from the zero scale, and hence it requires adjustment before using it. Another give reason, the resistance wire of the hot wire ammeter is stretched over a plate made of a material that had the same coefficient of expansion as the wire, the resistance wire. Okay, I explained this to eliminate the effect of the atmospheric temperature of the surroundings. So, once again, it is to eliminate the effect of the atmospheric temperature, okay, on the wire. In this way, the wire is kept taut, and the plate will expand by the same amount as the resistance wire of the device. And now we'll make, comparison between hot wire ammeter and the moving coil galvanometer. Comparison between moving coil galvanometer and hot wire ammeter. Okay, first point of difference. Moving coil galvanometer is based on the magnetic effect of the electric current. You can say it is based on magnetic torque. Okay, and what about the hot wire ammeter? It is based on thermal effect of the electric current. So one of them, which is the galvanometer, based on the magnetic effect, but the other is based on thermal effect. Moving coil can measure DC currents only. Moving coil galvanometer only measures DC currents, but hot wire ammeter, measures the effective value of the AC current and DC currents. Scale of the moving coil galvanometer is uniform. Theta is proportional to the current required to be measured, but it's not uniform in the hot wire ammeter. The scale of the hot wire ammeter is not uniform because theta is proportional to square the current, I squared. Talking about the moving coil galvanometer, the pointer of the device stops moving when electromagnetic couple is balanced by mechanical couple. And what about the pointer of the hot wire ammeter? It stops moving when the resistance wire reaches the temperature at which the heat produced in the wire, heat developed in the wire due to the flow of the current equals the heat lost by convection. Moving coil galvanometer, of course, it is very sensitive, so it has much, higher sensitivity. It has high sensitivity, but hot wire ammeter has much lower sensitivity. And now, disadvantages of the moving coil galvanometer. We'll compare disadvantages of both devices. As time goes on, as time elapses, the hair springs become inactive, slacken away, and the magnet loses some of its strength, so the device requires recalibration from time to time. So moving coil galvanometer requires recalibration from time to time. Why? Hair springs slacken and the magnet loses part of its strength. And what about the hot wire ammeter? Yes, its sensitivity is small. Talking about moving coil galvanometer, it only measures direct current. And disadvantages of hot wire ammeter is affected by atmospheric temperature. The pointer of the hot wire ammeter takes long time to measure the current and to return to zero scale. And now talking about AC circuits. Okay, AC in a non-inductive ohmic resistance. Non-inductive ohmic resistance or ohmic resistor. Non-inductive means we've got a coil, in which no an EMF is induced, simply because it is doubly wound coil. Okay, So ohmic resistor is denoted by R. When the circuit is closed, circuit shown in front of you, which is powered by an AC dynamo, the instantaneous potential difference, instantaneous voltage across the resistor is given by the relation, the voltage of the dynamo. Okay, so V instantaneous equals V maximum sine omega t. This is the first equation, where omega t is the phase angle. Dividing both sides by R, both sides of the equation, the previous equation by R, will obtain the following equation. The equation that gives the instantaneous current. Okay, so V over R, instantaneous voltage over resistance, equals V maximum over R sine omega t. V over R will give, yes, the current. So instantaneous current equals I maximum sine omega t. If we compare the two equations, equation 1 and 2, okay, we've got the same phase angle, omega t, in both cases. Okay, so voltage and current are in phase. So we draw both of them, yes, on the same line. Current coincide with the voltage. They are, yes, in phase. We've got the same phase angle. So from equation 1 and 2, the voltage and the current are in phase. And now AC in a pure inductance L, inductive coil of 0 ohmic resistance. AC in a pure inductance. Pure inductance is denoted by L. What is a pure inductance or pure inductor? It is an inductive coil of 0 ohmic resistance. So ohmic resistance of the coil, ohmic resistor, which is denoted by capital R, equals 0. In front of you we've got a circuit powered by AC dynamo, and we've got, yes, a coil, pure inductive coil. Okay, if we apply Ohm's law of a closed circuit, yes, the current through the circuit is given by the following relation. The current equals V minus L di over dt. L di over dt is the EMF induced by self-induction over R. So we can say the product of IR is equal to V minus L di over dt. Since R is equal to 0, I said, the ohmic resistance is 0, so we can say V is equal to L di by dt. I is the instantaneous current. And we've got an equation for the instantaneous current. Thank you very much. Yes, it is I instantaneous is equal to I maximum sine omega t. Okay, so what about the voltage? The voltage is equal to L. Yes, the first derivative of I maximum sine omega t. Okay. First derivative of the sine is cosine. Omega cosine omega t. Okay? So the instantaneous voltage will be equal to L I maximum omega cosine omega t. Okay, your attention. We'll do something here. The last equation can be written as follows. It is something very important. So V is equal to L I maximum omega sine omega t plus pi over 2. Cosine is converted into sine, okay, by adding pi over 2. So we can say V is equal to V maximum sine omega 2 omega t plus pi over 2, but I is equal to I maximum sine omega 2. If we compare the two equations, okay, we can say it is quite clear that the current in a pure inductance lags pi over 2, yes, behind the voltage. That is to say, the voltage leads the current by 90. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.